A friend comes and asks you, I'm seeing those bits in memory, what do they mean? The first instinct is to go and express that in decimal and say this is the number 162, but that's not the only option. Keep watching if you are confused. So don't let me confuse you, it can be 162, but let's see what I mean. If we look at this number, then again it can be 162 in decimal, and if we want to convert from binary to decimal, that's the formula, well-known formula that we use, but that's only true if we are looking at it as an unsigned integer, but it can also be, for example, a signed number or a signed integer in this case, and the MSB, the most significant bit, will tell us if that's a positive or a negative number. In this case, it means actually minus 34. It can also be representing a negative number, but this time in the 2's complement method, in which case this number equals actually minus 94. Or it can even be a fractional positive number, in which case it means 12.2. The left side is the 12 and the right side is the 2. It can also represent a floating point fractional, in which case it is a fractional, but there is a different method to represent the number. And by the way, nobody does 8-bit floating point, but this is just an example. Now the thing is, it's not necessarily even a number. For example, it can be this gray shade if you are using 8-bit grayscale, or if you are using 8-bit ASCII, it can be the cent sign. And you can even define your own meaning, and that's what an enum is. And in this case, it means a cat. So the real answer for the question, what are those bits, is that you need more information. You need to know what they represent in the context of your program. So in a sense, it's like switching glasses when looking at something. If you're looking through those glasses, you see one thing. If you're changing to those glasses, you see something different. If that rings a bell because it sounds a little bit like casting, that's no accident. If I'm telling the compiler, dear compiler, please take this char A, and now I want you to address it as if it is an unsigned char, then I'm asking the compiler to switch glasses in a way. And at the same time, I'm telling the compiler I want to address this as something that represents something else. When we do those perspective shifts, of course, it will have implications on how our program is dealing with our data. The simplest example to that will be the enum example. There is no meaning in adding a duck and a cat. But even if you're dealing just with numbers, the program will do different things based on the representation. And it goes as deep as to the question what the CPU itself will do with the representation. And let's see that in action. We are going to look at that through a very cool tool called Compiler Explorer. So on the left, I have some C code, and on the right, I have the generated machine code, and it will change immediately after I change something on the left side. So I'm starting from two variables, which are unsigned bytes, and I can see on the right that the div instruction is generated to implement the division on line 7. So what we're going to do now is to take A, and we're going to tell the compiler, I want you to look at A as if it is just a regular signed char. And as you can see on the right, now the code that is generated to implement the division is the idiv instruction, and this is the signed division instruction. So by telling the compiler that now A is representing a signed number, it has changed what the processor is going to do with it, and I'm going to get a different result. Another thing that is very interesting, that on the right now I can see that the compiler have added the instruction move SX, which is move with sign extend. And this happens because now the compiler looks at A as a sign number, and therefore it has to do sign extend when expanding it into the register. And if you compare it to whatever it's doing with B, you will see that with B, it's padding it with 0. This is move with 0 extend. So if your binary data represents or expresses different things, then generally speaking, the CPU will have to deal with the data differently. Let's see one more small example where it makes a difference. In this example, we'll see what happens when we shift a number. So we start again with two unsigned chars, And we can see on the right that in order to shift A to the right, the generated code is using the instruction shift right. Now, if I tell the compiler, please address A as if it is a signed char, we can see that now the compiler have generated the instruction shift arithmetic right in order to maintain the signness of A. Okay, so I hope I was able to convince you that binary data representation worth thinking about. Now, I see people confusing that with radix presentation. I don't really like to call that representation because if you look again at our number and you look at it through the glasses of unsigned integer representation, if you express it as a 162 decimal or a 242 octal or a hexadecimal A2, it doesn't really represent anything that is different. It's still an unsigned integer number, and it's the same quantity just presented in different radixes. In other words, if you have that many apples, it doesn't really matter if you describe it as 16 decimal, 20 octal, hexadecimal 10, or 10000 binary. It's not going to change the quantity or the quality of what you have. In order to describe the number of apples here, you will use an unsigned integer most probably, and the radix thing is more of how you present the number. Although you will find references to that also as representation, that's fine. I just want to stress that it's different than the different representations we saw before, in which each representation means something different. Just to drive home the point of the radix being just a different presentation of the same quantity, let's do a similar experiment again, this time with this super simple program, and we can see that we assign B with a hexadecimal 80, and on the right I have added the binary product of the compilation, and you can see that this hexadecimal 80 has found its way here. Now, if I replace hexadecimal 80 with 128, which is the decimal number equals to hexadecimal 80, you can see on the right that nothing in the binary product has changed, and you can still see here this 80 because the binary product is all being presented in hexadecimal. So nothing has really changed. Just to make sure things aren't too simple, there is also the notion of encoding. How does that mix up with representation? So encoding is how you encode things with bits. It's actually the specification of how you do things, a little bit different than representation in my view. So in order to summarize that, let's look at that table. So if we are talking about representation, we are talking about the what. What do we want to represent? So one example to that is character encoding, and another example to that is assigned integer. And then we have encoding, and the encoding is the how. How do we encode those things on the left using bits? So we have all those examples to represent character encoding with bits. And each one of those is a different method or a different specification of how you do that. Similarly, we can use all those different methods in order to encode a signed integer with bits. So what about radix presentation that we have discussed before? How does that fit into here? So if you have a quantity like a signed integer or something else like character encoding that is being represented by a quantity, and that's always the case with computers, then in different radixes you have different presentations to the same quantity, but you are not changing what is being represented, how it's being represented, or the quantity or quality of things. Okay, with that cleared out, let's finalize this video with a cool example where neglecting representation considerations can lead to hazardous results. In this example, we are creating an array with 256 cells, and B is initialized with 128, which is well within the boundaries of this array. But then we assign B into C, and C is an unsigned int, which means that B has to be expanded in order to be assigned into C. So the code that is being generated by the compiler uses mov sx in order to do this expansion, in order to maintain the signness of B. However, since I've initialized it to 128, it means that the MSB of the byte is set, in which case the sign extend will have to fill everything to its left by ones, and that creates a huge number. So later on, when we use C in order to address the array, we're not going to get 128 here. We're going to get a huge number and spill out the end of the array. Now let's run this code. In this version of the code, I have initialized the array to be all zeros, and I'm also initializing D to be all ones, so later when we read from the array, we will see how it changes. So I start running, and you can see that our B equals hexadecimal 80, and that means that the leftmost bit, or the MSB, equals 1, and therefore C has all those FFs because it was sign extended into an int. And as you can see, that's a huge number. Now D will step one more step, and we can see that D now equals all those FFs. And allegedly, if C was 128, we would be reading zeros now into D. But when we step again, you can see that D is not reading from within the range of the array. This is because, again, C is a huge number. Alright, I hope you have enjoyed this video. Maybe it have cleared out some things for you. If you like this video, please hit the like button and also subscribe to this channel because there is more coming up. See you.